Hello viewers, today we will talk about the design of stator winding of a synchronous machine. The stator winding has single-turn or multi-turn coils arranged in the slots to obtain the required phase groupings. The arrangement of the winding should be such that the EMF induced in all the phases are equal in magnitude and frequency. The EMF of all the phases must have identical wave shape and should be displaced from each other by 120 degrees. Single layer winding and the double layer winding are the two types of windings which are used in a synchronous machine depending on the requirements. A double layer winding is used more over the single layer winding because it has certain advantages. So first let us look at the advantages of double layer winding over single layer winding. So we look at the advantages of double layer windings over single layer windings. So the first point is, in double layer winding, better EMF waveform is obtained using a short pitched coil. So let us write it as better EMF waveform by using short pitched coils. Now as we are using a short pitched coils, that means the length of the end connections is also reduced. Therefore, the second advantage we can see is savings in the copper which is used for making the winding. Since all the coils are of the same shape, fewer winding tools are required. Thus, it reduces a considerable cost of manufacturing of the stator coils, and hence we can say we have a lower cost of coils. As discussed, the coils are alike and hence it becomes easy to manufacture. So let us write ease of manufacturing the stator coils. The last and the most important point is fractional slotting. Fractional slot winding can be used, which would further improve the EMF waveforms. These were the few advantages of double layer winding, but there are also a few disadvantages of double layer winding over single layer winding. So let us look at the disadvantages. The first major disadvantage is it is difficult to repair. Difficult to repair. If a certain part of the coil is damaged, it becomes very difficult to repair that damaged part. Next is difficulty in insertion of last coils. Lot of difficulty is experienced in inserting the last coil of the stator winding over one pole pitch. Moving to the next disadvantage is comparatively wider opening slots compared to the single phase winding. So we'll write here wider openings of the slot. For proper insertion of the coils, wider slot openings is very essential, which also gives rise to the noise level. Because of the insulation between the layers, the last point is poor space utilization. Poor space utilization in the slot of the stator windings. So the space within the slot is not completely utilized, or let's say have a very poor utilization factor in double layer type of windings compared to the single layer type of windings. Next we'll focus on the number of slots of the machine. The number of stator slots should be selected very appropriately, as it affects not only the performance of the machine but also affects the cost of the machine. Since there are no definite rules, let us discuss that what could be the advantages and disadvantages of choosing the larger number of stator slots. So let us look at the larger number of stator slots and focus on its advantages. Point number 1. As the leakage reactance is inversely proportional to the number of slots per pole per phase, we can say that the first advantage could be considered as reduced leakage reactance. The second advantage can be taken as lower internal temperature, because more space between the conductors is available for the circulation of air. So the second advantage can be written as lower internal temperature. And thirdly, we can say that since we have large number of slot, there would be less tooth ripples, so lesser tooth ripples could be observed. Now let us focus on the disadvantages. So the first disadvantage is a large number of coils to wind, insulate and insert in the slots. This would result in a costly machine, so we can take the first point as higher cost of the machine. Moving ahead, the teeth becomes mechanically weaker if we increase the number of slots. So the second point can be written as weaker mechanical teeth. Because of the larger number of stator slots, we would have narrow teeth and therefore there would be a higher flux density in the stator teeth. There are some other factors as well which should be kept in mind before designing stator winding of the synchronous machine. Points such as the ampere conductor per slot should not exceed ampere conductor per slot should not exceed 1500. The last point to keep in mind for designing the stator winding of a synchronous machine is the slot pitch. The slot pitch for a low voltage machine should be less than or equal to 3.5 centimeters. Similarly, the slot pitch for a machine up to 6 kV should be less than or equal to 5.5 centimeter. And lastly, for the machines up to 15 kV, the slot pitch should be less than or equal to 7.5 centimeters. I made a wrong symbol here, so let us rectify the symbols. Slot pitch is less than or equal to 3.5 for a low voltage machine, less than or equal to 5.5 centimeters for a machine up to 6 kV, and slot pitch should be less than or equal to 7.5 centimeters for a machine rating up to 15 kV. So considering the advantages and disadvantages, the ampere conductors per slot as well as the slot pitch, the number of slots for a stator winding could be decided. The number of slots per pole per phase of a salient pole machine is taken as 3 since it has a very huge number of poles. Whereas in case of turbo alternators, the number of slots per pole per phase is taken between 7 to 9 as the number of poles are fewer compared to the salient pole machine. The number of slots per pole per phase can also be taken as a fractional value as it reduces the magnitude of higher harmonics in the EMF waveform, but it should satisfy the ampere conductor per slot condition as well as the slot pitch condition as discussed before. Now let us focus on how the number of turns per phase are calculated. Turns per phase are calculated. So as you know, the generated EMF per phase, that is EPH, is given by 4.44 into F into kW into phi into TPH. Now what we require is turns per phase. So making TPH as the subject of the equation, TPH is equal to EPH divided by 4.44 F into kW into phi. The variable phi, which is nothing but the air gap flux per pole, can be given as BAV multiplied by pi dl upon P. For full pitched coils, the winding factor kW can be assumed as 0.955, but this is only for the full pitched coils. The number of turns calculated should be rounded off to an integer. The final figure of the number of turns per phase will be obtained after making proper arrangement of these conductors in the stator slots. The air gap flux per pole should be modified as per the final figure of the number of turns per phase. In the next topic, we'll see certain formulas about the dimensions of the stator slot. The flux density in the stator teeth at the gap surface is given by Bt, which is equal to phi divided by small bt multiplied by Li multiplied by Nt, where Nt is nothing but the number of teeth per pole arc, whereas Bt is nothing but the width of the teeth. and BT is also given by, let us write down first, BT is the width of the teeth, and it is also given by phi upon BT into Li into Ni. That is just making BT as the subject in this equation. So this BT comes here. Also, we can find out the width of the teeth from the width of the slot. That is, if we know the slot pitch, then the width of the teeth can be taken as the slot pitch minus the width of the slot. In the next topic, we'll see the mean length of the turn for a double layer stator winding of a synchronous machine, which consists of, the first is the length of the coil in the slot. Each turn consists of 2 times the gross length of the stator core, as length of turn in slot is equal to twice the gross length of the stator core. So this could be taken as twice of L. The next point of consideration is length of overhang portion. Length of overhang portion. So the length of the overhang portion of the turn will depend upon the pole pitch of the machine. This portion of length of the turn may be taken around 2.5 times the pole pitch. The next point of consideration is length of straight portion extending from the core. The length of this portion depends mainly upon the terminal voltage of the machine. The length per turn due to this may be taken approximately as 0.05 times the terminal voltage of the machine in kilovolts. The next point of consideration is length of the end portion. The length of the end portion consists either of evaluate of the multi-turn coils or clips of the single bar coils, and it may be taken as 0.15 meters. So combining all these factors, the mean length of the stator turn can be written mathematically as LMT, which is equal to 2L plus 2.5 into the pole pitch plus 0.05 times the kV rating plus 0.15 meters. Now once we know the mean length, we can move to the resistance of the stator winding. So the resistance of the stator winding is given by Rs, which is equal to rho into Lmt upon A. Instead of A, we are writing here As. We all know that the formula for the resistance is rho L by A. Instead of L, we are writing here the mean length, that is Lmt. Here A is the cross section area given by As, and this would further be multiplied with the number of turns per phase, that is TPH. Hope you enjoyed this session. We would see the losses occurring in the stator winding in the next video. Till then, have a great day ahead. In case of any queries or doubt, feel free to comment in the comment section or reach out on the email address provided in the description. Thank you.